In this video, I'm going to focus on chemical formulas. I'm going to discuss and identify several different types of chemical formulas, and then also kind of how to interpret some of them. So first, I want to talk about something called a molecular formula. So molecular formulas are, as they sound, just the formula of the entire molecule. So let's take hydrogen peroxide, for instance, H2O2. That means that in a molecule of hydrogen peroxide, you have two hydrogen atoms and two oxygen atoms. There's another thing called an empirical formula. So the empirical formula is just the simplest or smallest whole number ratio of all of the atoms in your molecular formula. So it's possible for them to be the same. Basically, if you cannot reduce the subscripts to any smaller whole number ratio, then they would be the same. In this case, the ratio of 2 to 2 can be reduced to 1 to 1. So the empirical formula for hydrogen peroxide would be HO. There's another one called the structural formula. The structural formula actually shows the basic bonding motif. So it actually shows the connectivity between all of the atoms. So for hydrogen peroxide, we have something like this. So you can see that the two oxygen atoms are actually bonded to each other in the middle, and off of each one is one of the hydrogens. And using structural formulas, we can actually start to see something known as isomers. So isomers are different molecules with the same molecular formula. So for instance, let's say we have acetic acid. Acetic acid, which is just vinegar, actually. Vinegar is just very dilute acetic acid. Has the chemical structure this. Now this double line here, this is the first time you've seen this, but it's just a double bond. So whereas these single bonds have 2 electrons being shared between the atoms, a double bond is basically just 4 electrons being shared. So let's look at its molecular formula. So it's got 2 carbon atoms, so C2. It's got 1, 2, 3, 4 hydrogens, H4, and 1, 2 oxygens, O2. So that is the molecular formula for acetic acid. There's another molecule known as methyl formate. And the structural formula for methyl formate is as follows. Right. So let's look at the molecular formula here. We've got, once again, 2 carbons. 1, 2, 3, 4 hydrogens, and 1, 2 oxygens. So now, these are clearly different molecules. Here, we've got an oxygen between the 2 carbons. Here, that oxygen is outside of the 2 carbons, and the 2 carbons are actually bonded to each other. Clearly, there's a different bonding structure. These are absolutely not the same molecule. But they have the exact same molecular formula. So these are isomers of one another. So now I want to look a little further into ionic compounds and some types of ionic compounds that you'll see. So first let's look at these a little more, because I want to try to explain how to know what your formula is going to be. So let's go with NaCl, for instance. So if we are looking at a periodic table, main group metals have specific charges that they form. So group 1, lithium on down, will always form +1, no exception. If it's forming an ion, it's going to be +1. Group 2 are always going to be +2. Group 3, remember, starting at aluminum, because boron is not a metal, group 3 is going to be +3. For your nonmetals, noble gases do not form ions, so they are not going to be involved in these. Halogens, they prefer to form -1 charges. Fluorine will always be -1. The other halogens, if they're bonded to other nonmetals, won't always be, but if they're bonded to a metal, a halogen is always going to be -1. If bonded to a metal, oxygen's group is going to be -2, nitrogen's group is going to be -3. Right? What makes transition metals special is that transition metals can form multiple different charged states. They're metals, so they're always going to be positive, but they can have multiple different types of positive charges. So if you're dealing with a transition metal, you have to use what it's bonded to figure out what its charge is going to be. So let's look at, first though, NaCl. So we've got sodium and chlorine. Sodium is in group 1, so that's going to form a +1 charge. Chlorine is a halogen, it's going to form a -1 charge. So if you're trying to figure out the formula for an ionic compound, you can always do just 2 steps. The first step is called crossing the charges, and then the second step is just reducing the ratio if possible. So what crossing the charges means is basically just take the number portion of the charge for each ion. So don't worry about the sign of the ion. Just take the number and you bring it down as the subscript for the other species. See, and that's where the crossing of the charges comes from. Now, remember, if you have a subscript of 1, you don't actually have to write it. So this gives us NaCl, each with a subscript of 1. And then again, you just look at the ratio of the subscripts, and if you can reduce it to a smaller whole number ratio, do that. Obviously, a ratio of 1 to 1 does not reduce, so that is your compound. Let's say, for instance, we have iron. Now, iron is a transition metal. So you'd have to be told, so if you're trying to figure out the formula, you'd have to be told what the charge is. So let's say we have iron, 2+, and oxygen, which is going to be a 2- charge. So again, you cross the numeric portions of the charges. Now you've got Fe2O2. Now, the ratio of 2 to 2, that can be reduced, right? 2 to 2 can be reduced to a 1 to 1 ratio. So you have to do that. So the actual correct formula, molecular formula, this is not just an empirical formula, this is actually the molecular formula. And the correct molecular formula for these 2 ions is FeO. Let's say we have a different form of iron. Let's say instead we have iron 3+ and oxygen 2- still. Now when we cross the charges, the 3 comes down here for oxygen and the 2 comes down for iron. So now we have Fe2O3. A ratio of 2 to 3, that cannot be reduced, so that would be your molecular formula. Now, let's say we are dealing with polyatomics. So let's say we have a molecule that looks like this. Cobalt. I'll stick with nitrate for now. So if you have a polyatomic, you need to put that in parentheses if you have a subscript outside of there. Because what this subscript of 2 means, outside the parentheses, is that means that you have 2 of these polyatomic ions in your molecule. So basically you have 2 of these nitrate ions bonded to this cobalt. Basically the 2 has to get distributed to everything inside the parentheses. That's why you need parentheses there to keep the polyatomic together. And remember, cobalt is a transition metal, and as I said, transition metals you have to sometimes determine the charge by looking at what it's bonded to. Right? So if I were to give you this molecule, and I said, what is the charge of cobalt? Well, you know, since nitrate is one of your common polyatomics, that it has a -1 charge, and this 2 right here indicates that there are 2 of these nitrate molecules. So you have 1, 2 nitrates, right? We have only 1 cobalt because there's no subscript here. So now the total amount of negative charge from the nitrate ions is -2, right? Because this one is -1, this one's -1. Add those together, you get -2. This is a neutral molecule, all right? Otherwise, if it wasn't, we'd see a charge for the whole molecule as a whole. So what needs to be the charge to cancel out -2? +2. So it's cobalt 2+. Right, and then just one other type of formula that you will see sometimes is something known as a hydrate. So hydrate is when you have basically a molecule surrounded by water. So you would see something like this. That's a 2. Okay, so we've got CaSO4 times 2H2O, basically. So that looks like times. Basically, what this means is that, so we've got these two water molecules, and although these water molecules are not actually bonded to any of this stuff here, they do coordinate to it, and they stay with it. So if you're looking at the formula for this, the water molecules are included in the formula. Right? So again, it just means that there's, so basically we have this calcium sulfate, which is the CaSO4, and you basically have two water molecules that very closely coordinate, but they stay with it no matter what, right? I mean, there are ways to separate them, but they stay with, so these are all kind of collectively viewed as a single molecule, and it's referred to as a hydrate. So if you're trying to figure out how many of each type of atom exists in here, you have to take it from this portion and from this portion. So there's 1 calcium, there's 1 sulfur, there are 2 times 2, so there's 4 hydrogens. Now there's 4 oxygens from this portion over here, and there's 2 times 1, so there's 2 oxygens from the water. Add those together and you get a total of 6 oxygens in this molecule, in this hydrate. And now, just one more example, determining the number of atoms in a molecule. Let's go with this. So, if I were to ask you how many of each atom exists here, for aluminum, obviously we just got 2, so that's its subscript. So now, I said that anything else, a number immediately outside parentheses, has to get distributed to everything inside the parentheses. So, if you have a subscript outside the parentheses, you have to multiply it by each atom's subscript inside the parentheses. Sulfur, has no coefficient or no subscript shown, so it's just 1, so it's 3 times 1. So there's 1 sulfur, or I'm sorry, there's 3 sulfurs. Oxygen. So we see a 4 here, which means that this is another one of your common polyatomics. It has 4 oxygens, and there's 3 of those polyatomics. So 3 polyatomics, each of them has 4 oxygens. So you do 4 times 3, there'd be 12 oxygens.